Welcome to Smart Materials microHVA product overview. Meet the next generation of battery-operated high-voltage amplifiers, the microHVA-2, a dual MFC channel high-voltage power amplifier. The microHVA-2 is a triple output power supply with one fixed 500-volt output and two variable outputs from 0 volt to 2 kilovolts. This power supply is specifically designed for microfiber composites. In this tutorial, we will go over its applications, the safety instructions, what's included, an overview of its functions, its 3 operational modes in greater detail, and the conclusion. The microHVA can be applied in many ways: on small UAVs like drones and flight control surfaces, on RF models, flight models, and ship models, on high-voltage power supply for piezoceramic and piezo-composite actuators, and last, applications requiring structural deformation or morphing in spoilers, rudders, valves, and more. Before operating the microHVA, please be carefully advised of its safety instructions. The microHVA generates voltages up to 2000 volts, which are present on both sides of the PCB unit and can be life-threatening if used improperly. Place the microHVA on an insulated base, which can withstand more than 2000 volts. Never place this unit on a conducting surface, and make sure you don't touch the unit while in operation. The attached cables need to be electrically and mechanically in good working order. Please do not use if there is any indication of them being defective. Replace the cables only with the high voltage amplifier switched off. Before removing the cables from the load, switch off the amplifier and wait at least 5 minutes until the load capacitors are discharged. The kit comes with a microHVA-2 printed circuit board, or PCB, which weighs about 50 grams, and its dimensions are 45 by 67 by 18 millimeters. Also included are 2 jumpers for setting the function mode with jumper K2. 6 crimp connectors are also included. These are for connecting the output cable to the PCB. An input cable, or control cable, with a plug for the input connector K1 for applying power and signals to the PCB, is also included. The 5 wires of the cable are color-coded to correspond to each pin. We will talk more about this later on. Now to the overview of our PCB board. This is the PCB's top and bottom view. Jumper K2 contains pins 1 through 4. Input connector K1 activates color-coded pins 1 through 5. The MFC is connected with negative connection to the bias, and the plus connection is to either output A or B. Both channels can be operated independently. You can, if you want, attach one MFC to output A and one to output B. Before heading into more detail, here is the general overview of the PCB's operational functions. The PCB has a DC power supply of nominally 12 volts, maximum 16 VDC. All input impedances are 15 kiloohms. Output A and B have the same ranges of 0 volts to 2000 volts, 0 milliamps to 1.5 milliamps, and maximum 3 watts output power, offering 4 modes of operation. The fixed bias output is 500 volts, 0 to 10 milliamps, and 5 watts. Be sure to keep the board at a temperature of 0 to 40 Celsius, with room or outside humidity no higher than 85%. There are 2 variable outputs, A and B. You can connect one or several MFCs in parallel to the output A and bias connectors or B and bias connectors. The optimal MFC to use for this experiment is a P1 type. Symbols plus and minus on the MFC corresponds to these connectors on the PCB. If you connect them wrong, the MFC will be depolarized. The voltage across the MFC ranges from negative 500 to positive 1500 volts, so a voltage swing of 2000 volts across the MFC. To turn on the PCB, first choose the control cable with the color-coded wires and attach it to the K1 connector. Now that it's turned on, you can use any control mode on K2. To choose any control mode, use 1 or 2 jumpers to place over the pins on the K2 modus. Placing the jumper on pins 1 and 2 will give you analog control mode, 2 and 3 pulse modulation, pins 3 and 4 the 8-bit I2C control mode, and using 2 jumpers, cover pins 1 through 4 to get 12-bit I2C control mode. Now that you know which jumpers to place over the corresponding pins on K2, you can go back to the K1 connector and choose the function. There are 5 pins, each coded in a different color to make it easier to differentiate. Pin 1, color-coded in black, corresponds to voltage supply ground. Pin 2, color-coded in pink, serves signal output 1. This includes analog 1, pulse width modulation 1, and I2C data. Pin 3 in brown serves signal input 2. This includes analog 2, pulse width modulation 2, and I2C clock. Pin 4 in green enables the signal. The microHVA is disabled if left open and enabled if connected to ground. Pin 5 in yellow controls the power input. The first operational mode we will cover is analog interface. If you're using an analog function generator, the jumper for the K2 connector needs to be inserted onto K2's pins 1 and 2. Pins 2 and 3 of the control cable connected to K1 are the 2 analog control inputs. The input voltage range is between 0 to 5 volts and corresponds to -500 to +1500 volts across output channels A, B, and bias. The amplification factor is 400. The signal frequency range is 0 to 250 Hz, depending on the connected capacitance and the voltage swing on the output channel. Take note that when out of range, the PCB interrupts the process. The board is over voltage and negative voltage protected. Our second operational mode is I2C interface. For this mode, you can use the 8-bit control mode or 12-bit control mode. To activate 8-bit, place 1 jumper over pins 3 and 4 on the K2 connector. Then connect pins 2 and 3 on the K1. To activate 12-bit, use both jumpers to cover all pins 1 through 4 on K2 for activation. If you want to control the microHVA digitally with a computer, the Raspberry Pi 3 generation is a good, portable option which can control the microHVA digitally. You can also use a laptop. Use the slave address 78 hex. Again, you can use 1 MFC per output or 2 on either output in parallel. Our third operational mode is the PWM interface. To get pulse width modulation, put the jumper onto pins 2 and 3 on the K2. Then insert your control cable in the K1 connector to get either signal input 1 or 2. Pins 2 and 3 of the control cable connected to K1 are the 2 PWM control inputs. The pulse voltage will range between 0 to 5 volts, with signals less than 3 volts treated as 0 volts. The repetition rate is nominally 50 Hz, but falls between 5 and 300 Hz. Here you can take a look at the PWM mode in greater detail. A pulse less than 0.1 milliseconds is ignored. Pulses from 0.1 to 1 millisecond are treated as 1 millisecond for minimum output and will produce -500 volts. Pulses from 1 millisecond to 2 milliseconds correspond to -500 to +1500 volts across the output channels and bias. This is the operational mode. Pulses from 2 to 5 milliseconds are treated as 2 milliseconds. Pulses greater than 5 milliseconds are ignored. For the experiment, you can use this formula to achieve maximum achievable frequency measured in Hertz. This is calculated by adding 5 nanofarads, the power supply, to the capacitance of the connected MFCs per channel, or C. This table gives you a closer look of the performance you can get from each output channel. The more MFCs you add, the higher the maximum capacitance and the lower the maximum frequency. Less voltage results in less power and allows for higher frequency. For example, if your MFC's capacitance is 2 nanofarads, The maximum achievable frequency with a voltage swing of 2 kV should calculate as 35 Hz. With a voltage swing of 1 kV, it should be 70 Hz. Feel free to send us any feedback, questions, or comments. Our email to contact is info@smart-material.com. Our website is www.smart-material.com, and our Facebook handle is Smart Material USA. You will also find a complete manual on our website. Just follow or copy this link for the document. Thank you for using our microHVA product tutorial.